G'day viewers. In this segment I'm going to give you an overview of some aspects of the network layer, and we'll go into more detail in these aspects in the following lectures. Okay, so first of all let's look at where we are in the course. Well, we're starting the network layer. That's where we're at. And yes, this is IP. This is the unit in which we'll learn how the Internet Protocol works. As you can see from this reference model, we've gone through the physical and link layers, so you know how to send information and bits across a link instead of signals, and you know how to send frames of information across connected links. That's great. Now we're going to move on to the network layer. The network layer builds on the link layer, and its job is to have routers send packets of information across multiple connected networks. So let's see how that works. Well, actually, before we do that, one of the first questions I'd like to talk with you about is why we even need a network layer in the first place. Now, we've already seen with switches and links that we can build small-scale networks. So here's a small-scale network, and if we follow all of the ideas we've seen so far, we would be able to send frames from one computer to another computer that's connected somewhere to those switches. This is pretty good. If we can do this already, we should ask what it is that we're going to get out of a network layer, since a network layer would seem to be doing much the same thing in sending packets across all of the hosts and routers that are connected together across many networks. Well, I'm glad you asked. There were actually three shortcomings of the switch approach we looked at that I remarked on very briefly at the end of that unit, and I'm going to remind you of them now. The first shortcoming was that the method we looked at didn't really scale up to large networks. Now, as your network gets larger, it goes from tens to hundreds to thousands up to millions of different hosts. Think for a moment about how the switching approach would scale. A couple of things happen. One, there is a blow up of the routing table. So that's this situation here. Every different switch in this diagram is keeping a table which maps for every different destination which way to go. That table is going to have millions of entries with our switching approach as the network gets bigger. That's a lot. Everyone needs to maintain this table. A second issue is this broadcast. That's here. As you remember, to reach new destinations that they haven't heard of before, switches broadcast. This means that the first time you send to a new destination, it could get sent across the entire network. Imagine sending a packet to a new destination and having it go through millions of other hosts on the network just because you weren't sure which way to go. So this design doesn't scale as well as we would like. A second shortcoming is that the switch approach we've seen doesn't work across more than one kind of link layer. It's a link layer approach, so it's designed for a particular link layer. Now, we've already seen different kinds of links. We've seen Ethernet inside wired enterprises, 802.11 inside, many houses, and 3G for cellular mobile connectivity. They're different kinds of links from our point of view. We would like to be able to network them all together and send packets from, say, an 802.11 host through to a host on a wired Ethernet. But the switching approach we've seen so far doesn't really take this into account. It isn't equipped to join these different kinds of link layer technologies together. And a third reason is that switches don't give us much control over the routes which are taken through the network. The spanning tree algorithm we looked at is pretty impressive really, in that you can just plug your network together however you like, and the network will be able to find a spanning tree and get packets from any host to any other host. But it didn't guarantee that the paths which were taken were necessarily very good ones. So traffic in a spanning tree network might follow this path. Say from one switch to another, we might go along this path I've outlined, when in fact there was a direct link which would have gotten you straight there. That's not what you would necessarily want, because usually the most precious resource in a network is the network bandwidth on all of the links. We would like to use it well, and to do that we want to have good control over the paths that packets take through the network. So when we look at a network layer approach, we're going to see ways in which we can improve on all of these shortcomings. We'll look at ways to scale the network. Essentially, instead of sending to an individual destination, we'll be able to do all of the routing and forwarding through the network, all of the work at routers, in terms of blocks of IP addresses called prefixes. This is applying hierarchy so that all of these different routers will have smaller tables. They won't necessarily need to have millions of entries for millions of hosts. We'll also see in the network layer support for heterogeneity. IP uses an approach called internetworking, in which different link layer technologies are put together. And we'll study IP really as the big case example here, in which there's a lot of experience in what you have to do to make an effective network. And finally, eventually, we'll look at different ways of having better control over how you use bandwidth. Rather than the spanning tree, we'll look at lowest cost or shortest cost routing, which is a different framework for deciding which way to go. And eventually, we'll even look at quality of service, although that will come later in the course. Quality of service is really also about different ways in which you would make good use of the bandwidth you have. Okay, so this slide here gives you a topic list of what we're going to go through in this unit. It's fairly detailed, and I don't expect you to understand all of the terms here right now. You can use it as a roadmap for the units that will, or the different topics in lectures that we're going to go through in the different segments. First of all, I'm going to tell you about different network service models. As well as a traditional packet model of datagrams, there's also a virtual circuit model, so there are different possibilities for networks. Then we're actually going to spend quite a while going through different segments on IP. IP is the big example from which we can learn a lot about how to build networks, as well as understanding how the internet works. So we'll go through many different aspects of IP. And we'll cover all of these things, and you'll get to know what all of these ARP and DHCP and MTU and ICMP acronyms mean. So don't worry about it now, we'll go into it. This that we're going to look at, IP, is really IP version 4. That is the version of IP which essentially most of us probably use today with our computers. There's a new version of IP in the internet that's now being deployed, it's the future, and that is IPv6. So to finish up on IP, we'll look at IPv6 to find out what's different and what's going on with its deployment. Many of you have probably heard of IPv6 as something that's coming to the internet. And finally, in this unit, we'll look at NAT. NAT is a strange kind of forwarding technology. It's called a middle box. It is something that many of you probably have in your houses. If you have it inside an AP that you hook to the internet, usually has NAT technology inside it. We're going to understand exactly what it is, since it's something that many of you probably encounter day to day. And we'll see how it does fit, or rather how it doesn't fit, with the standard IP model. And then eventually there's this item down here that's grayed out for now, routing algorithms, which we'll get to in the next unit. There's actually a lot of detail in there. Routing is a big and important topic, but we're going to put that off for a while. Before we go ahead though, I want you to be able to be aware of one important distinction, and that's the distinction between routing and forwarding. They're two different things. It's a little confusing because routers in the internet do both of them. They're responsible for both routing and forwarding, so that's why I'm pointing it out. Now, routing is the process of deciding which way your traffic should go in the network. This is a process in which all of the routers participate. So routing involves talking to all of your neighbors and saying, hey, who's where, and do you know who's over here, and generally working out what is the best way, the best links you should use to send to reach all different destinations. So it's a network-wide process where everyone agrees on things. It's global, and because of that, it's relatively expensive. Forwarding, on the other hand, is the process of deciding what to do when you get a packet. Someone tosses you a packet, what do you do with it? You forward it by throwing it out the link on which it needs to go and doing a few other things. So forwarding, of course, uses the information that comes out of routing. After routing, you're sort of left with a table which tells you which way to go to get to different destinations. Forwarding is the act of using this table. This means that it's a process that happens purely at one node. It's a local process. And because of that, it's fast. Actually, it has to be fast because a router might have to process millions of packets a second. So we've got to be able to forward quickly. Now, our plan, looking ahead, is to treat these two topics differently. Actually, the first one we're going to do is forwarding and understand what routers do with packets. Now, logically, you might think that routing comes first. It's difficult to know how to forward a packet until you know which way they need to go. But we think that it will actually prove easier for you to understand the internet if we go through the forwarding model first, and then we deal with routing later. So I'm going to ask you just to suspend disbelief for now, and just imagine that routers somehow magically know which way to send packets. What we're going to look at in the upcoming segments is how they actually send those packets on their way, because there's quite a lot involved in that. Okay, now that we've got this distinction in mind, let's go for it and find out how the internet and IP work.